And this is in collaboration with people at the APS and the Materials Science Division at Argonne, including Ray Osborne, Matt Krogstad, Guy Jennings, Stefan Rosenkranz, and some others. And by hybrid HPC workflows, what I mean is we're going to glue together commodity computing systems like people's laptops or whatever they bring to the APS to do their work with HPC systems like Theta and eventually other large near exascale or post exascale computing systems. Oh, that doesn't work. Oh, I do? No, I'm just trying to go to the next slide. But I guess that doesn't work. Okay, yeah, so what the overview of my talk is, I'm going to talk about a little bit about the data collection that Ray and his team do, how they set it up, and show some example data sets. Then I'll talk about the data analysis and the transformations that we're interested in computing, and that's really the rate limiting step when they're trying to collect data. That's the crystal coordinate transformation. Then I'll talk about our HPC workflow solution, which involves the GUI side and the distributed computing side on Theta. So as far as data collection, they have a Dexter's Pilatus 2M set up as shown here. This is this is the sector 6 beamline at the APS. They're typically cooling things quite a bit and rotating the sample in there automatically, and so they'll go from one sample to the next at a range of temperatures and different rotations. Some examples of the materials that they've done over the past few years are shown here. The important illustration out of this is just the breadth of materials that can be captured with this technique. So they're doing diffuse scattering. They're looking at various short-range orders in the crystal structure, where you have especially disorder that gives unique properties to these materials for batteries, solar cells, and a variety of other applications. The setup is kind of shown here. There's a little movie of how the sample is rotated as it's being data is being collected. It's in a continuous rotation. It ends up collecting data in kind of this unusual coordinate space. So the computational part we're going to talk about in a minute is really transforming it back to a standard grid using CCTW. They collect data at a rate of 10 frames a second, which adds up to about 3 terabytes a day. So it's definitely quite a bit of data, and it's pretty dense data. As I showed on those images, they're looking at not just the peaks, but really the area in between the peaks is what's interesting to the application. So there's quite a bit of data, and as you probably have heard, the APS is being upgraded. So over the next 2 years, it'll be much brighter. And if the detectors improve and so on, they're going to be collecting at least 10 times as much data per unit time. So we really need to scale up the computing to make that possible. This is just another illustration of the density of the data. Thousands of Bragg peaks, many Boolean zones, and so on. So as far as transformation and analysis, we start with the data in the NeXpy Python toolbox. This is an extensible toolkit for visualizing and analyzing data that comes out of this setup. It lets you rapidly scroll through a HDF file that's in the NeXus format, look at all the metadata and everything like that, very quickly produce plots, and it's got this IPython shell in it, so you can quickly get to the data sets programmatically and use tools to do analysis interactively. Also, since the data is in the NeXus format, you can pull it into other tools and quickly look at things that like what is shown here, where you can quickly see the metadata tree, quickly make plots and other things like that. What we need to do is connect that data visualization and analysis to the computationally intensive part, which is the CCTW application developed by Guy Jennings over the last few years. This is written in C++, so it's not pure Python. It scales in terms of computing cores, so it uses Qt threads to parallelize on a single node. When the data set sizes that we are producing, we really need to. This is really the rate limiting step. So we can get to a situation where we're backed up visualizing the data at this step. What this step really does is it takes a range of different rotations of the same data in 3D. So this is essentially 3 different dimensions on the same data. So now you have these gaps because the detector rain, and then basically they stack them all together and do a weighted average, and then they want to do the transformation on that. So there's some orientation and other stuff like that that need to go in that are a little bit manual, and you can generate a backlog of work. So the idea is to, once you have things queued up in the GUI, we want to be able to submit them to Theta for analysis. So Theta right now is the biggest machine at Argonne right now. It's 4,000 compute nodes. They're all Intel KNLs. Quite a few cores are available because there's 64 cores per node and 4 threads per core. It's 12 petaflops total. What we're looking forward to over the next just few months, hopefully, is that Aurora will be online. This is going to be just a much more powerful system with beyond 2 exaflops of computing power. Of course, it is going to be a GPU-based system, so we might need to get ready for that. The workflow system we're running on Theta right now is SwiftT, which is the system I developed. This is an MPI-based workflow system that's designed to run on these very large systems. It's designed to distribute work very quickly, and it's designed to run tasks that are written in Python, but also directly call into tasks that are written in C or C++ or Fortran through native library interfaces. So that makes it a little bit unique. It's not quite like other workflow systems. It's very oriented around this HPC model. The NeXpy system has a workflow manager built into it as well. This allows you to construct this table that's kind of shown there, where you can see all of the samples you've collected and the various stages that they're in as the checkboxes progress. That's backed up by a database, and it basically allows you to tell it what you want to do, queue things up for execution, and then they go into a queue, and then you can see the logs that come out of what's been done. But this needs to be ported to the Theta system, which was not part of the original design. So the use case here, again, as I've kind of teased at, is that basically we're collecting all of this data, like I said, gigabytes and terabytes. There's some semi-manual processes of calibrating it and orienting it for analysis and transformation. We stream it from the beamline to those supercomputers automatically with Globus. That's pretty much a solved problem. But then now we need to distribute the work with the SwiftT workflow. And our solution is to plug it into a Python queuing system called PersistQ. That's a third-party Python library. So now we can actually run the GUI over X. You have the data stored in GPFS on the supercomputing site, and then you can queue things up using that workflow manager. The task gets serialized and put into this queue that is portable and also readable from the compute nodes of the supercomputer, so that the SwiftT workflow can simply just pull tasks out of that queue and distribute them. And basically, once that's been done, it's a solved problem in terms of the scalability, because SwiftT can handle quite a few tasks. And this is all actually orchestrated with, or it's really implemented with Python, because all the queuing is done with Python. So we think it's a pretty portable and also scalable approach. Some of the code snippets are shown here. On the GUI side, this plugs into a plugin into the NeXpy toolkit that gives you this file queue capability and plugs into the rest of that refinement workflow I showed. That was the checkbox and the grid. But the new stuff is shown on the right. This is the SwiftT workflow components. These are just the snippets of it that are in Python. The overall workflow is about 50 lines of Swift, but the Python segments are shown here. They basically are strings of little snippets of Python code that are querying the queue and then distributing the work. And distributing the work is simply executing CCTW command lines that have been constructed by the GUI across the system. So in conclusion, we illustrated an end-to-end automated data transformation and analysis workflow. Again, it was just a kind of a single workflow, but we think it can be generalized and scaled, generalized really and scaled to other problems that need analysis. That's kind of a similar thing. So it demonstrated an integration of two paradigms: the Python GUI world, where you're kind of running things on your laptop or whatever, and this MPI-based Hpc workflow world. And here's our acknowledgements. Thanks. I can take any questions. Thank you very much. Yep. Questions? Yes, please.
Hi. So typically on cluster, you have a resource manager, or something, which has its own job queue and queues MPI work and so on. Right? So you have a task queue and you take care of MPI distribution yourself. Does this mean you are looking to replace whatever Slurm does by your workflow manager and just use Slurm to access the HPC nodes, or is it somehow supposed to work together with the resource manager on the cluster?
Yeah, so the question is about resource managers on existing clusters and how we would work with them and whether or not we're trying to replace them. We're not trying to replace them. Swifty deploys itself using any existing workflow manager. So any existing resource manager like Slurm and PBS and Cobalt and things like that, or just plain SSH-based MPI systems. That's all fine. That's kind of something that's built into Swifty. And the new part is really just connecting that to the outside world over these queues. So it's totally compatible with existing resource managers. Within the Swifty workflow, you basically are able, Swift will get an allocation on these systems, and then within that, you use the Swift programming language to build a workflow that can do many, many tasks. And that's kind of the snippets that I showed a little bit, although I didn't show the whole workflow.
Well, MPI is made for parallelization over CPU code. How will you port your code to the GPUs? As you mentioned, that the next generation of all next generation HPC system will rely on GPU.
Yeah, the question is about MPI and GPUs and how we're going to port to that. So in terms of the workflow solution, there's nothing really that needs to be changed there because it's just an MPI-based workflow language. The CCTW part will need to be adapted for GPUs. Right now, it is a CPU-only code, and it's going to need to use those GPUs. So that's going to be at that C++ level in the CCTW code.
So for working with HPCs, it's always very important to work out how many cores you actually want to use to get the optimum performance. Have you checked to see if that's the same goals for the system?
Yeah, so the question is about how many cores to use and to do some kind of performance study there. I don't think we have done a thorough performance study. This integration with Theta and CCTW is new. They were using a commodity cluster before that. So we haven't really looked at the optimal core count on Theta for this. Theta has 64 cores. In theory, we could use less. Maybe there is some performance benefit there. But in practice, they do use all the cores. And I think they've seen the best performance that way on the existing cluster they're using. Did that answer the question about performance, or is there something further?
I was thinking if you say a single crystal versus, for example, a power node, the single crystal would scale better to power performance.
Okay, so there's an idea that different experiments might produce different performance. Again, that's probably outside of the scope. I am not the developer of CCTW. However, I think that it does operate on the data in kind of a dense mode of operation. So I would my knee-jerk reaction is to say that it wouldn't matter what's in the data because it's looking at all the data anyway.
Okay. So
all right, thank you.
Again,
yeah.
Justin. And I close the session here. Thank you.